Hi friends, I'm Rahul. Welcome to my channel, Anveshan Labs. Today we are going to discuss about one of the very powerful machine learning algorithm for the classification and regression. The name of that algorithm is support vector machine. It's very useful, and hope you will like this tutorial. Okay, let's start with. I will just go through the my Git repository. Here you will find in the README file all the flow of this tutorial, how we are going to proceed with this example of the support vector machine and the data set I'm referring. Okay, so let's go one by one. The environment here I'm using in this tutorial is the first one I'm using is there is a data set. The data set is pumpkin seeds. These are the it will get the properties of the pumpkin seeds, and I am referring that this one data set from the Kaggle database. I have given here the link as well. The second step is we have to install the Python package for the Kaggle to to for get Kaggle standardized API to access the dataset and and dataset and other properties. The third one is like I'm using here VSCode as ID environment. Let's start with step by step. So, friends, let's discuss with the first example. First of all, to start with any algorithm or machine learning, so data is very crucial part, and we have to look at database, a data set where we have to keenly look into the properties and how the data is, how its orientation, how the structure, and how what are the important features and fields that we need to see or we need to study, and we observe the data set first. So, guys, this is the photograph of pumpkin. It is considered as one of the vegetables, but it is botanically it is a fruit. And you see, this is the pumpkin, and the database is about the seeds of this pumpkin. Yeah. So let us see the data set on the Kaggle. So this is the website where you will find the data set, pumpkin seeds data. So this data set has around 2,500 rows, and these are the statistical information for the features. Okay, so detailed, compact. These are the name of the columns, area, perimeter, convex area, etc. This is the data, and let's go to the column and see the statistics of the column. So like area of the seeds, this is you can see it's a valid data of 2,500 rows. There is mismatch, missing values. Mean value is 80.7, standard deviation 13.7K. Like perimeter, you can see convex area, solidity. You see the mean value is 0.99, standard deviation 0. Like quantiles, 25% quantiles 0.99, and you can go through this in detail in this data set. And on this particular data set, we are going to see the classification technique by support vector machine. So we see uh, the first step, data analysis uh, and quality of data, statistical features of the data. Okay, so we saw this on the online. Next thing is the retrieve data from the given data set and cache it into the development environment. Guys, here I have placed all these four uh, coding files. We will find it here as well, these coding files into my environment. Okay, so this is uh, where I have kept this programming files. So this is the serial number 1234. Okay, so let us see how the things happen here. So this program actually connects to the with Kaggle. It refers to the Kaggle datasets, and it extracts and caches the data into a zip pickle file, which is Python pickle file, one of the format, right? And what are the libraries that you need, right? So basic libraries like you will need a Kaggle API, like pandas, okay, SHUtil and shoplips. So basically, this code is we are establishing one of the location where we can cache this file. So we will cache this file into the data cache. You will see here. You see here is the pumpkin seeds PKL file, and in this the file name where our dataset data will be cached. Uh, that is it will pick up to the data frame, and let us see how it happens. So it is loading from the cache. We have a Kaggle API. It will authenticate your Kaggle. Okay, and this is the database reference, dataset ref. This is download directory, and you see like temporary directory it will create, and the code download dataset. It will start downloading the dataset, and this is zip file. Okay, so this basically this code is like to find the downloaded zip file and extract it, and extract and create a data frame from the Excel sheet. We have that data set as part of Excel into the data set, Kaggle data set, and we will cache it, and it will save the data into the it will save the data into the cache file name. This is the cache file name, right? Pumpkin seeds pkl, and once you save the data set into the pkl file, right? So pumpkin seeds, this is the cache data. Now the data is completely at our end. Hey guys, after this, we will see the next step, that is retrieve data from the given set and cache. We have seen this, so we have completed the first step. We have gone through the Kaggle data set. We have seen the statistics of the columns of the data sets, and we have retrieved with the help of Kaggle API and retrieved the data, extracted into a PKL file. Okay, so this is how we have cached the data. Now we'll proceed with the third step, that is like to standardize the data. We have once we go through the data, okay, like we have a lot of features involved into the data set, so we have to standardize the data and understand the features of pumpkin seeds and how this will happen. Let's check out. So guys, let's go ahead with our next code snippet. So that is in the and to feature PCA 2D. Here we are going to observe the features of the data set, number one. Number two, we are going to reduce these features into the like uh, low dimensional components like principal component analysis, PCA, so that we can focus on the less details of the data and more into the analysis details. So how this will take place, let's see. So this is the file. Okay. To study the support vector machine, you see, we are going to use the sklearn model selections, SVM preprocessing, metrics, and decompositions, like PCA. And this is the standard libraries that we are going to use in our code in this code snippet. So this particular code, this is the basic understanding of the features with principal component analysis and with the true component dimensions of the feature, and we will also visualize the 2D visualization of this particular data set. So let's start with this is the libraries that we will need. And for sklearn preprocessing, we have to do the standard scalar, encoding the labels. You know what is label in the data sets. We have train data, we have test data, we have given data, and we are supposed to predict the class of the data. So there are two classes of the pumpkin seeds. So we have to encode these two. There are two values of the pumpkin seeds data. We will check this one. Okay, so this is the data set, and let's go to the label. So these are the label. Okay, this is class. These are the two classes for the pumpkin seeds. Okay, so this is first of all this particular function load cache data. This loads the data. We remember we have created one pickle file, which is cache data. So from this cache file, data file, we are going to load. Okay, if that cache file exists, we are going to load that into the data frame. So what we will return the data frame. Okay, and where this the function we have written the data. So this entire particular data set came into this data frame. So label encoder, like instead of is we have remember these are the classes. So we are going to encode this particular class into so that it will be useful. This encoding will be useful and able to it will be able to easy to understand. So we have to encode. So we have encode this particular class, right? So uh, class is the column of the data set. Okay, so it is the label column, and we are going to encode it. Okay, so there are two classes. The one of the class is 0, another one is the 1. Okay, so this is the class distribution. You can see we will run this one. How the class distribution happens? It means how much of the data belongs to a particular class, like 0 or class 1. So we are going to see that into we are going to plot with the help of the matplotlib pyplot. Okay, so this is the visualization package that will help us to visualize the things. Okay, guys. So let's next go with the next things. This is one of the very important study of the SVM algorithm as well as we can say data. So what is correlation matrix? We have the properties of the pumpkin seeds where we are about to see how the properties are related to each other. Like, the seeds are oval, the seeds are round, and its color, their measurements of the axis, right, shape, and how it appears. So these are the features of the pumpkin seeds. So these features are dependent, not in the sense of dependent, but they are related. So there are two approaches of correlations of the features of the data. That ते correlation मध्ये डायरेक्ट पॉझिटिव्हली प्रोपोर्शनल असतं आणि त्याच्यामध्ये निगेटिव्हली प्रोपोर्शनल पण असू शकतं. What is positively proportional is like if the value of something, a property, is increasing, the value of the other property uh, affects as well in the positive way. So, like there is positive correlation, negative correlation. We will see that one. This is the code snippet to establish the correlation of the features, right? So, like we are going to build a heat map to study the correlation of the features, okay? And and then we are going to uh, like standard scalar. So what is a standard scalar? Standard scalar is like standardizing the feature values in order to like you know it will have a standard uh, variance of the values where it will benefit, like the mean we will keep it to the zero and the standard deviation will be one. So that our data, it's very good to understand the overall values of each feature and to standardize it, and it will be easy to acknowledge and understand the properties of the pumpkin seeds. So that is why we do the standard scalar. यामध्ये डेटामध्ये आपल्याला जे व्हॅल्यूज सापडतात प्रॉपर्टीच्या, त्याला आपण स्टँडर्डाइज करतो. स्टँडर्डाइज करणे म्हणजे काय, एका पर्टिक्युलर पॅटर्नमध्ये तो व्हेरियन्स, व्हॅल्यूज व्हेरियन्स आपण घेतो आणि त्याला आपण प्रेझेंट करतो. इट विल हेल्प, याला आपल्याला अंडरस्टँड प्रॉपरली इव्हॅल्युएशन करायला मदत होते. And we will see that how the standards scalar happens, right? So once we do that, we get the x scaled. So we've hit the scalar. Then comes the PCA. So we are going to see this one, how the things happen here, right? Yeah, friends. Let's see with the next thing is like this one. So, guys, we have seen standard scalar. The scalar helps us to bring the values of all features into one scale, one uniform scale, so that it will be convenient and easy to understand this. The, the next part is very important, like principal component analysis is one of the feature understanding tool. See, we have many features into the data. Like if we see, we have many features like there is area, perimeter, measure, manner, axis, you know, diameter, eccentricity, solidity, roundness, right? No, etc., etc. So what happens is like here comes the importance of principal component analysis. So it gives us an edge to understand, can we group the similar kind of features and its orientation, which gives us a common understanding of the features. फॉर एक्झाम्पल पंपकिनमध्ये आपण पंपकिन सीड्सचे जे फीचर्स आपण पाहतो त्याच्यामध्ये काही असे फीचर्स जे सेग्रिगेट करून एकत्र करून त्याला ग्रुप करून आपल्याला एक कॉमन अंडरस्टँडिंगमध्ये ते फीचर्स अंडरस्टँड करता येईल का. फॉर एक्झाम्पल साईज. तर साईजमध्ये काय काय त्याच्यामध्ये त्याचे मेजरमेंट्स जे फीचर आहेत ते त्यामध्ये कुठले येतील. And it helps us to understand not to go into the more details, only get the primary features. So from this entire 13 columns, if we choose that my component analysis will be the of the 2 degree, it means it will divide all these 10 features or 13 features into the two main categories, right? So that it will help us to understand, right? So that is the concept of principal component analysis. It reduces and minimizes the extra details that we don't we not into the granular level. We will not go into the granular level, but we will superficially understand how the features are related and categorized and grouped. Hey guys, let's see. This is the columns. This is our code, and this is the code of the principal component analysis. Let's run this code. Okay. So yeah, here is output and run this. Let's wait. Yeah, guys, the program has successfully run. So let's see one by one. What's the output of this program? So first one is like, we are about class distribution. So there are two classes. This particularly represents the class. This is the first class. This is the second class. Okay, so these are the number of values. This is the count of values, right? And this is the count of values for the class 2. So let's go to the another figure. This is the correlational matrix. So let's see that it will be serial. Okay. So here you see that there are features like area, perimeter. Okay. So this correlation matrix, this is the code that we have developed for correlation matrix, and we have got this one. Okay. So here, if you see, like if we study, this is uh, the this particular brown value gives us the strongest positive correlations. And as we go to the other part of the color, you see it's a blue one. Okay, so it's blue one that will give us the inverse correlation of the two properties. So, for example, if we see the compactness and eccentricity, like right, so it means that more eccentricity means the shape of the seed, like it's is it round, is it oval, right? So uh, like if we see that if less elongated, means the roundness, if you see the eccentricity, the, the more the compact the seeds, okay, the more compact the seeds, you will find the less eccentricity. Eccentricity means like uh, uh, elongated, you know, like big oval shaped seeds. So that is the feature of eccentricity. So more the compactness, you will see the less eccentricity. Lesser the compactness, you will see the more eccentricity. So this is the inverse correlation. The same example, if we see there, it's a positive correlation between compactness and roundness, right? So more the seed is compact, more it will be round, right? So that is the conclusion we can derive from the positive correlation you see. So value is 0.9, right? The compactness and roundness, the value is 0.9. So it's a positive correlation. More the compactness, the more the roundness you will see, more the compactness you will also. In opposite to that, we have negative correlation with the eccentricity. More the compactness, you will see more the seed shape as oval or elongated shape of the seeds. Lesser the compactness, you will see the more rounder shape of the seed. Right? So this is how we have to look the correlation of the columns. Hey guys, so this one is the graph. Okay, this is the two-dimensional graph of the principal component one, principal component two. So these are like we have grouped some of the features into the principal component one, other features into principal component two. These are the two classes color code, right? So this is the color code like zero for zero, what is blue, and for one it's green. So these are the data points. So this is principal component analysis visualization for function seeds. This is the variance you see of the two features. Right? You can correlate this, and this is the 2D dimension. Let's see how we can see into the three-dimensional space with the three principal component factors of the same features of the pumpkin seeds. Hey friends, let's move ahead with the next part. So we have jumped to the third section of the principal component analysis. Right? So we are about to see the 3D visualization of with the 3 degrees of the components derived from the features. Okay. So understand principal component analysis with three components, features and 3D visualization with refer pumpkin seeds data set. So this is the all code we have seen, standard encoding of the class, standardizing the values, and PCA for the features. Here, is the component to know the featuring. So there obviously there will be a question like which features are going to which component of the analysis, right? So we like we have three degree of the PC. So we are like regrouping the features. Okay, those are meaningful to particular concept, and those features we will regroup, and then we will do the analysis of these features together. So here the degree is third degree of the PC, and you see this is the code where we have original feature names, and we have binding to the particular component analysis here, and we have done the plot of we have we did plot the those contributions of the features to the analysis, right? So, like, what are the top features of that goes to that particular PC1, PC2, or PC3? So that particular record also we will maintain, and I will show you how that things will happen. So this is the all like enumeration, and this is how the scheming factors for the graph one. So we will run this one particularly, this particular code, and let's see the output. Okay. See, this is loaded the graph. Okay. So before that, we'll see what it has done. See, so what you see here is the successfully. So this is the principal component analysis 1, 2, and 3. So what you see here is the contribution. For example, this is a feature compact, right? So how much this particular feature is contributing into this group, that is PCA, right? So like compactness is there is like more contribution to this particular component analysis. Okay, so it gives us analyst to focus on which of the group of features to focus on to study into the graph. So that is the usage of PCA. So after this, we have got feature contribution principle. Let's see this one. Let's see one by one. So this is how the contribution is happening, right? So like minus 0.8 to positive 0.4. So now if you see uh, this brown color patches, right? So the more you see the brown color patch, the more the contribution of that feature to that component analysis. Like here we see 0.3, 0.3. So this component analysis one, right? So this is principal component. In this principal component, these are the features like 0.3, 0.1, like area, perimeter, major axis length, convex area, and like width diameter. These are contributing this particular component. These features particularly contributing more to the component analysis one. So this is how it makes easy instead of because it is not necessary there will be 10 or 13 features for a particular data set or a study. There may be many features, and PC will help us to focus on the important features together. So that is the beauty of PC. You see, so like here in PC3, uh, what are the features and at what percent they are contributing, at what value they are contributing to that component analysis. Hey, so let's start with this is the diagram we have seen. Let's close this one and study this later. Check this one. Okay. So top features into the component analysis one is this like perimeter compactness. So these are the like major contributors. These features, these three features are major contributors to this component. These three features are major contributors to this component, and we have plotted PCA analysis here. So this is the three-dimensional. You see, this is PC1. So total contribution like 49 PC to 34.0, C3 8.7%. So these are the two classes 0 and 1. So this classification of the seeds with 0 and 1 is how the 3D analysis. So these are these are the values of the features, and these are categorized in the in the three groups. So how it visualizes and how we can see how the data points are calibrated here. So this is the 3D visualization. Right? Okay, so let's start with the next file. So guys, this is very important file. Here we are going to demonstrate and study the support vector machine, how it is modeled, and how we are going to predict the classes, right? And then we are about to check the accuracy as well as we will see how the predictions are made are there, how many right predictions are done, how many wrong predictions are, right? So we are going to see that through the confusion matrix. So what is confusion matrix? What is the accuracy parameter? We'll see shortly. So if you go through this particular file for SVM, this code, let's use the code one, right? So let's be after the standard scale. So X is nothing but the train and the uh, uh, like we have labeled column and we have featured column. So X belongs to the, when we say X, these are the featured columns. When we say Y, these are the label columns. Label column means we are about to do the predictions and results onto the label column. Right? So like we have to train, we have to prepare a training data set. This is a supervised learning process. We are preparing training data set, test data set, along with labeled one and X train, X test, Y train, Y test. Right? This is the code. We have, once we've done the training of this data, okay, we'll run this code shortly and we are what we are expecting. Okay, so this is where the important part. So training starts. Okay, so how the training starts here in the support vector machine. As we know, there are three different kernels. Like the modeling of the support vector machine, there are three to four different, basically, the Bs, right? For example, there are two classes, right? So in the two-dimensional space, it's very easy to identify and segregate the two classes. Like this is class one and class two, right? So if you see that now, what if we have something, the classes, the classes that resides here. Okay. तर यामध्ये आपल्याला ट्विकिंग करावं लागेल, राईट? So here we need to tweak. Here we have to prepare some of the models, right? So like this models, like there are linear. So this is the linear way of getting into the classification, right? So there are other kernels like linear, there is polynomial. If you see the polynomial, it helps us to rigorously see this one. So in that case, this particular algorithm, this will help us to calibrate, for example, like this. So it will help us to get the this one. It will help us to get a particular support vector. So what is support vector? The points that lies on this margin. This is called as margin. The the points that lies, like for example, see, and the points that lies on this particular thing. If this is the class 0, it's like here. This one also lies on. These are these particular boundaries of the data sets are called as support vector. It helps us to identify how the margin is to separate the classes, right? So in polynomial kernel we see there is more easy and effective way of classifying the data, right? Uh, Similarly, we have another kernel that we have radial basis function. Radial basis function is also like tweaking. So if we are doing some changes into the margin, right? If we are uh, turning the factor, so overall the margin tweaking, how it appears, right? So we are going to try this kernels and check how the classification accuracy actually affects. Okay, let's see. Here, we'll choose first of all the radial basis function kernel. So radial basis function kernel is that we will frame. Okay, this is the we have fit uh, the data into the model, and we did the prediction. So once we pass this one, and we'll do the predictions. Right. So like one test, we find the accuracy score. Okay. So we have standard functions to check the accuracy scores of the classification. So basic SVM accuracy, it will evaluate the accuracy. So what is confusion matrix? You know what is confusion matrix? It's easy to diagnose the positive, true, negative, false. This is how we can see here, and we will plot layout where we will present a confusion matrix. So let us run this and see the output of this particular program. So here you will see. So we are using radial basis function as support vector machine kernel. And if you check this one, we have got the accuracy for this particular model is 0.877, right? And this is what we got the confusion matrix, right? We see here on the x-axis we have predicted levels, right? Okay, so this is what the algorithm has predicted. This is what the algorithm has predicted. Okay, for this class, this is what the algorithm has predicted. What is actually in the data, right? Here we see we have a data. We have a data like that. So we prepare a data like that, and see. So this is the feature class. Okay, so we can say these are the features. The label class. So what happens here is we do, and this is the training data. So this is what we can see, right? And this is what is our, right? So you see, this is our training one, and this is our this is the feature one, and this is our test one, right? So this is the test data. This is the test section. This is the training section. So we in the entire data set we provide some for the training. As in this is the supervised learning. So this is the training section. So we will provide this particular all this for the training. Then we'll give this one these features for the test, right? These features for the test, and here are the we are going to cross check here. Here we are going to cross check the predictions with the actual. values. Okay, we have actual values for this, but we here only we are going to provide the features, that is training, right? And check actual predictions with the existing values, right? So this is how it works. So see, so with this particular kernel, for this particular class, this for this the true labels, and for this predicted. So 352 predictions, right, were correct for this, and 54 54 predictions were actually this one, but it has predicted class 1, right? 54 data points of the pumpkin seeds have this class, 54 data points actually, but it has predicted the class 1, right? Similarly, actually this one here, true positive, right? So true label is there are 38 data points which are predicted this one, this class, but they are actually this class. Okay, so this the confusion matrix helps us to understand how the prediction and how there is a variation and difference between predicted values. Okay, so out of that 355, 352, it has predicted the first class and was actually first class. 306, it has predicted those seeds as a second class, and those were actually the second class. Now, if you check with the first that we have used is the RBF, okay, radial based function kernel, and we'll run this program with the linear kernel and check the output. Okay. So it's training, so support vector machine, and let's see the output. So we have got the earlier using earlier with the RBF kernel, we have got the accuracy 0.8773. Here we have got the accuracy 0.8787, right? So you see there is a difference. Earlier using in this we have true positive predictions. We have 306, right? And there was something like the 352, right? So this is how there is a difference, right? So, but it is overall calculation for the true positive, true negative, false positive, right? And considering all these quadrants, we come to the conclusion of the accuracy, right? So let's see with the third one. You can see the third this one, and we'll run this. Save and run again. This is polynomial kernel, right? Remember we have discussed this polynomial kernel. So here you see, you can see 0.838, right? The basic support vector machine accuracy. So you can observe the difference. So once we change the kernel, once we change the model, right? So we can see the difference of the prediction of the class, right? So guys, I hope you have understood uh, support vector machine, and earlier to that we have discussed the correlations of the features, the statistics of the data sets, and correlation of the features along with the principal component analysis part of the features, and then we have trained and tested the support vector machine for the classification problem. I hope you have understood this tutorial, and if you like this video, please subscribe to my channel. Thank you very much.